Okay, this is the final exam review for GIS 101 for the fall semester in 2019. So, always know the basic stuff like what is geospatial data and specifically things like data information, that sort of stuff. So what does all this have to do with geography? Depends on who you ask. But we know that spatial data it's more than just data and information. It's something that we can understand. It has to do with a location. Often there's attributes, lots of sources, and lots of formats. We need to know what a datum is. It's a basis of a geographic coordinate system. That the Earth is not really round, it's more roundish. Vaguely roundish, it's actually quite oddly shaped. So what we do is we take an ellipsoid, which is basically a squished ball. So if you take a beach ball or something and press down the top and sort of mash the top and bottom flat, that's what we're talking about. Ellipsoid's still a perfect mathematical shape, so we can use it. But first we have to look at the geoid, which is this gravity-based surface that we consider the surface of the Earth. And we have to figure out how we can fit that to that ellipsoid. And so we move it around and make it fit. And once we make it fit, we call it a datum, because that's what it is. It's an ellipsoid that has been fit to the geoid. And there's a couple real common ones: NAD27, NAD83, and WGS84. Transformations allow you to change from one datum to another. This illustrates what I'm talking about. The ellipsoid is this perfect mathematical shape. The geoid is this gravitationally defined sort of mean sea level kind of a concept, and then the actual topography of the Earth is the sort of red line here. Geographic coordinate systems. It's basically a global system designed to tell you where you are. It works in lines of latitude and longitude. Latitude run parallel to each other. They're even distances apart. Longitudes run pole to pole. They're closer at the poles and they're furthest away from one another at the equator. The equator is sort of that middle line. Prime meridian is where we start measuring from left to right. We can measure in degrees, minutes, seconds, or in decimal degrees. Time zones loosely follow these to a certain extent. Looks kind of like this. Map projections are the next phase in this. When we're dealing with a geographic coordinates, that's angular degrees, and that's a round. It's coordinates for on a globe. Essentially, map projections are for projected coordinate systems, a PCS. This is where we take that still roundish GCS information and convert it into a flat map. When we do this, we generate distortions. This is not a new concept. In 1569, Mercator developed a really good projected coordinate system, and it was primarily used for navigation. The downside of it is it distorts sizes. Okay, it's a cylindrical projection. There's also other ones. There's azimuthal, conic, universal, transverse Mercator, the state plane coordinate systems, and others. So if you want to know how they work, imagine you took the planet, shoved it down in a clear plastic pipe, then looked through the side and drew on the clear pipe what you saw directly behind it on the globe, and that is a cylindrical. If instead of a pipe you used a cone or a flat window pane piece of glass, that would be an azimuthal. And here you see what we're talking about distortion. This is a cylindrical Mercator projection. And I want to point out the size of Greenland compared to the size of Africa. They look about the same size, when in fact Africa is about 17 times larger. So that is a distortion of size. UTMs, universal transverse Mercator, cylindrical projection, Mercator type projection. So instead of the cylinder going up and down, we run it sideways, left to right, and we divide the Earth into 60 zones. Each zone is 6 degrees wide. That gets us all the way around the planet. Here we can see how in a particular zone, like zone 13 north, it covers 6 degrees from 102 to 108. Everything between 102 and 108 would be relatively accurate within this zone, if in this projected coordinate system. These are the state plane zones. They're different. State plane zones, some are UTM, some are actually conic. But ultimately, they're for smaller areas, not these 6-degree zones. They're for state or sub-state level mapping. We do occasionally have problems when we try to go from one thing to the other, and it's more pronounced when you look at these maps of larger areas, like for example the entire continental US. If we look at a Mercator projection versus a Lambert conformal conic projection, you can see how they don't look exactly the same. So if you want to go from one to the other, you have to reproject the data. It's not a great big deal as long as everything's in the same datum. If they're in different datums, then you typically have to use a transformation to shift from one data to another, but that's the only real issue. In general, a bigger problem is when you have missing spatial references. Georeferencing is when you take a picture, an image, or a map, and you relate known locations on it to known locations on a layer that does have spatial information, and you use that so that you can then basically line up this and fix it so that it will then display properly. We do this using something called control points. We identify obvious features in 2 different images, one being one that does have spatial reference and one that does not. And so the control points is where they're basically just paired combinations of here's the corner of that building, here's the corner of that building, here's the corner of that parking lot, here's the corner of that parking lot. And then when you have enough of these, you can then create spatial references for the other item. So that ultimately you find these locations like this, and then things just line up. How do you do it? Well, the images have to either be rotated, skewed, scaled, or translated. We measure how accurate they are by the root mean square error. Rotation looks like it's turned. Skew looks like it's bent. Translation just means it's moved, and scaling means it's sized up or down. Ultimately, it takes the map that you have to the data that you know is correct, and it bends it and twists it and warps it, much like it does this old hand-drawn map that has been scanned to a current projected version of Eastern Europe and Northern Africa. Okay, so once you've done this, what do? Well, you have a couple options. You can update the georeferencing on the image, or you can rectify it. If you rectify it, it creates a new image where you have to resample. You get some distortion, some blurring, and some smoothing. And it'll come out looking something like this. I want to talk next a little bit about GPS and GNSS, Global Positioning System, or a Global Navigation Satellite System. These are essentially the same thing, but the GPS is the name for the American GNSS. So there are other GNSSs, but there's only one GPS system. The GPS system is ours. The GNSS system includes the GPS system and any other satellite navigation systems. They all work off of a constellation of satellites. This part of the satellites in space is called the space segment. They typically make 2 trips a day, preset orbital paths. The network of ground stations that monitor these positions and transmit corrections back are called the control segment, and then the individual person with a GPS receiver, or a GNSS receiver if you will, is considered the user segment. Works kind of like this: ground station, satellite, information transmitted back and forth. What gets transmitted? Something called the almanac. It's the information about the satellites, its orbit, and its location. And there's the ephemeris, which is more detailed information. Ultimately comes down to the codes, the CA, the P, and the Y. CA is course acquisition. This is a rough location. P code is the precise code. That's the very accurate military grade level location. And Y is the encrypted code, which is just a copy of the P code that you can't hack. And so if it's different than the Y code, if the Y code is different than the P code, you know somebody's jacking with the signal, and that's called spoofing. How does it work? Satellite tells you, ooh, you must be here. But really, here is kind of a big spot. And so, it might be anywhere within 50 miles from Ann Arbor. Well, you know, okay, let me back that up. It, from one satellite, will tell you you're 50 miles, for example, from Ann Arbor. But 50 miles from Ann Arbor can be anywhere along that circle. The second lock might tell you that you're within 150 miles of Traverse City. Again, another big circle. These circles intersect, and so you really know there's only two places that meet both of those criteria: 150 miles from Traverse City, 50 miles from Ann Arbor, and that would be Flint and Lansing. Pick up a third satellite that tells you you're 60 miles away from Kalamazoo, and now it only intersects with one of them, and this is what we call trilateration or triangulation, and it then identifies the location where we're at. Now, the problem is it gives you two locations, because these signals are not two-dimensional locations, they're three-dimensional locations. If you want to know the exact location, including your elevation, you have to have a fourth satellite. Otherwise, with three satellites, you get two spots. One is likely on the ground, and one is likely in the air. If you want to know the exact elevation of your spot, you need a third satellite so that you can figure out which of these two is actually the surface. Now, Desert Storm, back in 1990 range, actually did a lot to increase the availability and access to GPS in general. At that time, an off-the-shelf GPS meter was not very good. Today, most off-the-shelf are within about 15 meters accuracy. If you enable the WAAS setup, which we'll talk about shortly, that gets you down to about 3 meters, or 9-10 feet. Now, prior to the first Gulf War, so say before like 1990, 100 meters was about as accurate as you could get with a GPS unit, because they had something called selective availability. And it was a military level built-in accuracy that prevented others from using our system to accurately identify locations. During the Gulf War, we had a lot of soldiers. They were trying to navigate through a terrain that we were unaccustomed to some extent, and they were doing so with military-grade GPS systems that could bypass the selective availability. But it became apparent as the coalition forces got together that they had nowhere near enough GPS devices to provide as many of the troops with them as they wanted to. And so the solution was to give them off-the-shelf ones and to turn off the selective availability so that they would have full access to accuracy. And boy, did everyone love that. Now, after it was over and they sort of wanted to turn it back on, it was kind of problematic. But eventually, by about 2000, it had all been turned off for good and permanent, and then everything kind of worked great after that. And this has enabled this explosion in all this GPS, GIS, geo-related everything that's happened since then. Still, we have problems with the signal. It can be interfered with. The most common interferences are the atmosphere, because it can delay or distort or alter the path of the signal, and so we monitor for that. Earthly things also create problems: canyons, buildings, barns, you name it. If a signal can hit it, it could be a problem. Then there's PDOP. PDOP is the positional dilution of precision, and basically your satellites should be spread out across the sky. If they're too close together, it doesn't give you as accurate a result. And then there's this concept of a multipath, which is what happens when the signals begin bouncing off of objects, like, for example, a canyon or a barn or a pickup or whatever. And the signal that you pick up isn't coming straight from the satellite, it's coming off of an object and bouncing. So it's making the path longer, which then in turn skews your location. And so here's what we're looking at: signal coming down from space, hits part of the atmosphere, the signal gets altered in the ionosphere, and then it hits the troposphere and comes on down to the receiver. We measure it, we know how far away the satellite is, we know a correction, we can send that back up. When we have a multipath, it works like this. Signal comes down, hits something like barn, bounces over to receiver on the tractor. It thinks instead of just the distance of line 1, it thinks it's the distance of line 1 and line 2, which then makes the location incorrect. Because ultimately, the way all this works is, it's all timing and math. Signal leaves with a timestamp. It's 12 o'clock. You get the signal, and your receiver says it's 12 o'clock. The time on your receiver says it's 12:01. You know 1 second has passed. If you know the energy, the frequency, and all that stuff for the signal, you know exactly how far it can go in 1 second. And then that is the distance from the satellite to you. Now, if your signal bounces off something in this example like the barn, obviously that 1 second isn't a true measure. I want to talk about differential GPS, or DGPS. It's a system that provides positional corrections for GPS. It uses fixed known positions to adjust the signals and eliminate these pseudo range errors, which is, things caused by interference. It's important point of note that the DGPS correction improves the accuracy of position data only. So how does it work? Like this. We get the signals, we figure out what's wrong, we send out stuff. The SBAS is a satellite-based augmentation system. It sends corrected information above that the DGPS system sets up. It sends it back up to the GPS satellites, and a good example of that is WAAS. WAAS is a wide area augmentation system. It's a network of ground stations that monitor and calculate corrections across the U.S. They send the signal back up from these geostationary satellites and these earthbound hard reference locations. Knowing the path, it knows exactly what's going on, and then so if it knows it's off by how much, it sends the signal back up to the satellite and says correct your feed by this much, or send out a correction with your feed by this much, or it sends it out anyway. Ultimately, your handheld or your automotive or your cell phone GPS picks up that signal and says, hey, we need to adjust these numbers by this much to account for whatever is interfering with the signal today. And you end up with this. So what can a GIS do? The big things are analyze, capture, create, manipulate, store, and visualize spatial data. Discrete objects are one form of things we look at. The world is basically just a series of fixed objects with defined starts and stops. That's what discrete objects are. It is or it is not. We represent this a lot of times with vector data being points, lines, and polygons, points being locations, lines being one-dimensional objects, polygons being two-dimensional areas. Here are points and lines and polygons. Think about discrete objects. A good idea, the way to think about that is like the bounds of a football field. You're either on the field or you're not on the field. If you draw a polygon around the field, that polygon is a discrete object that represents the field. You're either in the polygon or you're not. Another form of data we use a lot is raster. Raster is a cellular grid-based design where each cell represents a fixed area, and all the cells are the same size. And here we have a bunch of information. At the top we have all these lines, and the bottom we have all these areas. These areas could be polygons. They could also be raster cells if this is that kind of data. So the object view is not the only way to look at the digital world. We can look at raster, and raster does tend to work best with continuous fields. And so every cell has one value. Cell sizes are the same. It's laid out in a grid. The best way to visualize it is think of pixels in a digital picture. Here's a bunch of grids. There's a bunch of cells. That's what a raster basically is. Here's a nice example of the National Land Cover data set where every cell of this area has been identified as one of these types of lands, land classifications. Both vector and raster contain attributes. Vectors capable of and designed for storing many attributes. Attributes are stored in tables, and your data comes in several types: nominal, ordinal, interval, ratio. Nominal is things like unique IDs, ID numbers. Sequence really doesn't matter. Ordinal data is ranked higher to lower, better, worse, but it's not a distance thing. Interval distance, or interval data, is a distance between is significant, but it's not like a fixed zero. So it's kind of like temperature. You can get below zero. Ratio data is number with a fixed non-arbitrary zero. For example, age, you can't be less than 0 seconds old. When we look at our data, here we have polygons on the right, we have attributes on the left. In the attribute table, we have fields, that being the columns, and we have records, those being the rows. Metadata, all you need to know, metadata is data about your data. It's organized by the FGDC, and they basically have this committee that explains what everything must be, and there's a certain list of what it has to have. It's got to have a description of the data. It's got to have accuracy information. It's got to have information on how the data is organized. You need a spatial reference information. You need entity and attribute information. And lastly, distribution information. Some of the earliest spatial analysis that we know of occurring, that's documented, was when John Snow mapped cholera deaths relative to the water source from where the people drank in 1854, and he identified which pumps, public water sources, he believed to be contaminated with whatever was causing the cholera. And he basically asked those questions, like how many people drink here, how far away from this pump do people drink, that kind of stuff. By asking various questions, he was able to figure out that people were being infected with cholera because of the sources of water, because some of the water was contaminated basically from sewage. Spatial analysis is the most intriguing and remarkable aspect of GPS. Using spatial analysis, you can combine data from multiple sources. There's a comprehensive collection of spatial analysis tools that extends your ability to answer all kinds of questions. You can do statistical analysis to look for patterns and make sure that they're real and that they're significant. You can analyze layers and calculate suitability to figure out where things should go. You can detect change over time. GIS enables you to address critically important questions and decisions that are beyond the scope of simple visual analysis. And that's what makes GIS special. So how do we get data out of our data? Well, one way to retrieve it is something called a query, which is where we basically ask a question of our data set. We do this using a language often called SQL, which is structured query language. We can ask binary questions, things like ones and zeros, yes, no, does it meet this criteria or not. We can do spatial queries, and we can select all the data within a distance of an object or within inside of something. We can create buffers, which define an area as a distance from some object, or we can dissolve things. There's all kinds of stuff we can do. So let's look. A query is a lot like shopping. SQL is the way you make your list about what you want, that puts it in your cart. Spatial query is like shopping for things based on what's there. In other words, instead of going in with a list of what you want, you would simply say, I want everything within 30 meters of the center of the fruit aisle, and so you go to the fruit section and you get everything that's close to that, spatially defined, not based on what it is, but based on where it is. Buffers find things based on an area as defined by proximity. Here we have a road going across the country. We put a buffer around it by some distance, and we can use that to then select everything within that distance from the other object. Queries find things based on some common attribute. For example, here we have the state of Ohio, and we have all the counties in the U.S. An additional field was the state, and so if you want to know what Ohio looks like, you can literally just go and select all the counties that are within the state of Ohio, and then you get this. You can also use GIS to solve problems. Maybe you need to know how many cities are impacted by this particular road. This would identify all of them. Maybe you want to create a polygon for the state of Ohio, so you select all those counties and then you dissolve based on the field state, and all of a sudden, boom, Now you got a polygon for Ohio. Sometimes complicated problems are just that. They're complicated and they require complicated analysis. So we take multiple GIS layers of data and we combine them in something called an overlay. There are a couple of different ones that are pretty common: intersect, identity, symmetrical difference, and union. You can look at the pictures here and see what they mean. For example, intersect is the data that is only common to both data sets. Symmetrical difference is sort of the opposite of that. Union is all the data from both data sets. We can also do something pretty clever called geospatial modeling. It comes in basically two flavors: simple and complex. Simple is just doing basic overlays, maybe a couple raster calculations. It's a real neat, clean kind of analysis. But the more complicated stuff is when we create complex spatial models, and we use techniques like weighted overlays, and we even use mixed methodology to combine things like index models and binary models to create complicated environmental process models. And here's a nice example. And so looking at the picture on the left, the question would be which raster cell, which square has trees in it? The top one, the top left, top right, bottom right all have trees, the other one does not. And so that would be the scoring for trees. And the bottom one, we're looking at water. The first one on the left and the bottom on the left do not have water, but both on the right do, and so you would get that. And so that's simple, asking a binary question of the data to generate a raster GIS. You could then combine these two, whether you add or multiply, to get different things, to figure out, what pictures have trees and water. Now if you multiply them together, you only find out which ones have both. If you add them together, you find out which ones have both and which ones only have one. We can also do this, do some fancy raster analysis. We can measure distances from objects. This distance raster, anywhere on that space that you point, you know exactly how far you are from a city. And you can scale it. You could combine various distance layers and create a suitability index. There's tons of different data that's out there, all of which could be converted into some useful means to help you solve a problem. Remote sensing is probably the part that everyone gets the most excited about because it sounds like it's the coolest. It's really probably the most work. Basic staples of remote sensing. One of the big ones is change detection. Here we have a map, and we're looking at 1980, 1995, 2020, and 2040. In a scenario like this, you would look at growth and create some sort of an equation that would then identify whether the growth is expected to continue, and then from that create a predictive model that shows the increase in growth over time. Basic stuff we do in remote sensing: number one is classification. Two common techniques, supervised and unsupervised, are just different means of identifying what every cell in a raster is. We can also use remote sensing as a means of data development. We take aerial photos. We then create polygons and lines over buildings and roads. We can also identify what's new as a means of identifying change. We can identify what something is by looking at the spectral indices. In other words, how the energy is reflected or absorbed by the object to determine what it may or may not be. And sometimes we use unique combinations of electromagnetic information outside of the visible spectrum, because that allows us to see certain classes of things more clearly. And then of course we use hyper and multispectral stuff, which is all electromagnetic energy based identification. When we're designing maps, what are the elements of map design? Well, there's a bunch. Here's 7. Scale bar, north arrow, legend, titles, fonts, layouts, and templates. You can go back and look at the lecture slides that I've posted a review for the final if you want to go through and read what each of these is if you're not sure what a scale bar or something is. We make a lot of different types of maps. There are 4 types we sort of talked about a little bit in class. A reference map, which gives you location information. A thematic map, which conveys a particular theme. Graduated symbols. It's a type of thematic map, but it shows changes in that value across an area. And then a choropleth map, which is another type of thematic map. It typically uses colors to show what your data looks like once it has been classified. Speaking of data classification, a lot of times when you want to display data, it's best to group it into classes, and how you do this is important. Some techniques are arbitrary and some are mathematical. The correct choice is driven by the data and what you're trying to convey. A couple of techniques we're going to talk about is natural breaks. It clumps things together and it separates things that are not alike. Quantiles use the distribution to place stuff in classes from low to high, where every class has the same number of participants. Equal interval breaks on a numeric scale, for example, like every 10 or every 100. Standard deviation is similar to equal interval, but it's based in terms of numbers of standard deviation is the interval. We can also normalize our data, and this is a means of correcting for other things that could be influencing it. For example, if you're trying to figure out, what state has a housing problem, and you just look at the number of unrented space, you might think, well, that will tell you how much available or not available new properties are. But if it doesn't take into consideration population, you might turn out that it looks like you've got a lot of houses, but given the population, you really don't. So normalizing it is a way of utilizing another field to sort of correct for things like that. When we talk about colors, the red, green, blue, or the cyan, magenta, yellow, and black are the other another common one, and they're just how we identify the makeup of a color. In general, if you've got a single variable, you pick one color and use a color ramp where you go from light to dark. If you have multiple variables or classes, for example, you have class data, multiple colors tend to work best. Here's what we're talking about: a single U color ramp versus a multi-U color ramp. So if we ask what is remote sensing, it's a process of collecting information about frequencies of electromagnetic energy absorbed or reflected from an object at some distance, i.e. remotely. This would include things like photographs, satellites, spy planes, any kind of number of senses, and anything other than sampling and analyzing an object in person. If we look at the timeline for how this all kind of gets started, Gaspar Felix Turchon, also known as Nader, began in 1858 taking landscape photos near Paris. People immediately begin thinking, this is awesome, we should use this for maps. By 1860 we have some photos in Boston from James Black. By 1906, George Lawrence, using a kite, took pictures of San Francisco immediately after the earthquake and fire. In 1903, the Wright brothers flew the first aircraft, and by 1908 they were taking pictures from airplanes in France. World War I rolled around, and all of a sudden the ability to do reconnaissance, in other words to figure out what your enemy's doing, where the troops are, where the trenches are, was really important, and it helped plan attacks, and we began doing that from aircraft using photographs. So here are some of the ones we talked about earlier. This is Boston in 1860 from a balloon, San Francisco in 1906 from a kite, trenches in World War II. I'm sorry, I meant World War I. Not all uses of remote sensing information have always worked out maybe for the best. Some of the information we collected nearly started World War III. It also probably prevented World War III. For example, they were able to identify areas in Cuba where nuclear missile sites were being built, and we basically stopped that. and it nearly started World War III. However, had we not done this and they had fully set these up, the Soviet Union would have had a capacity to take out all of our nuclear weapons and render us nuclear inert before we could launch, and that would have likely gave the Soviet Union at that time a reasonable reason to consider a first strike attack. So could have almost started, probably did prevent. We're just lucky there has not been a World War III. This is the SR-71 Blackbird. It was not developed by the X-Men, contrary to what movies might let you think. It is a spy plane of the highest order. Not only do we use aircraft, we also use unmanned aircraft. It gives us nearly unlimited flight time and ability to hover over areas and take pictures at different angles and at different times. It's quite useful. Not all of them are that big. They also have small units like this size that soldiers can launch and actually use it in immediate time-sensitive recon, figure out where troops are positioned or maneuvering during times of conflict. Lots of options for using various remote vehicles to increase our ability to collect data. So let's talk about the types of aerial photos, a little bit of science here for a change. If we're looking straight down, to point directly below the camera, it's called nadir, and it's named after that French fellow that took those early pictures around Paris. When we talk about panchromatic film captures all visible light, everything in what we call grayscale. So everything is from the darkest to the lightest is from 0 to 256. Color infrared is a special film in that it actually sees infrared. It's great for spotting things like green tanks that are trying to hide and pretend to be bushes. If we have color infrared film, we can create these other band combinations and replace, for example, some of the colors with this infrared that we can't see, and then it allows us to see things that absorb heat differently, or you know, in the case of a tank that's been driving around for hours, it has parts of it that are several hundred degrees different in temperature than the surrounding area. This just shows some of the way some of the film works. Don't pay too much attention to this slide. Here we've got a nice false color infrared where we've used that near infrared red and green in place of blue, green, and red. And what this does is it allows certain things to really light up, in particular healthy vegetation. Now when we have these aerial photos like this, scale can be a problem because you can't tell what things are. Because when you get high enough, everything basically looks like a spot, but if you were to move in closer, you would realize that some of these things are still farmland and they're center pivot irrigated ag land, but there's also other things that could be potentially. Image problems, terms, and facts. Principal point, that's the center of the photo. It's the spot that everything appears to lean away from. And that leaning away from that center point, that principal point, is called relief displacement. It's the distortion of objects. Ortho photos have had all the distortion corrected so that for every pixel it's as if you're looking straight down. NAIP is a good source of images. It's the National Agricultural Image Program, and they've basically flew around and took pictures of all the farmland. An oblique photo is taken at an angle, not straight down. There's the principal point. Notice how the buildings appear to kind of lean out and away from that. Not everything is all math and computers and remote sensing. We also look at things like patterns, the physical arrangement of objects, sight and association, what you see and where it's at, size, how big things are. Shadow, we can look at the shadow and we can tell by the length of the shadow, if we know the position of the sun, we get some idea of how tall things are. We notice shapes, certain shapes, like these round spots in the Midwest that are center pivot irrigations, and other places they would not be assumed to be that. Texture is the differences in certain shadings or colors. Tone is particular to the grayscale. All in all, there's this process called photogrammetry, which is basically nothing more than obtaining measurements of real-world objects from images. We have to know all the scale stuff, and we have to calculate the distances on the photo and the distances on the ground. And from that we can do some simple math, nothing more complicated than things like the tangent calculation you probably learned in 10th grade. And from that we can begin to figure out how tall things are. Basic concept of how remote sensing works: sun shoots energy down, energy hits stuff, some of it is reflected back up. The remote sensing satellite comes along, it's measuring what's reflected up. Now some of that energy is also absorbed, and some of that energy is also passes through, but the part that's reflected is what the remote sensing satellites look at. So when we talk about electromagnetic energy, remember it moves in waves, and the wavelength is the distance between the peaks, and the frequency is the number of peaks per unit time. Here's an example of a short wavelength and a long wavelength. Now, from that, we get the electromagnetic spectrum. The part that we can see, the visible light range, is from 0.4 to 0.7 micrometers, and that is where we go from blue to green to red. Below that, gamma, X-rays, and UVs. Above that, infrared, thermal, microwave, radio, etc. Different objects have different signatures. They have this combination of materials and makeup that cause it to reflect different things and different wavelengths differently. Across the x-axis on this chart we have the wavelength, and across the y-axis we have the percent reflectance. And so the higher the number means that more of that particular energy is bouncing off. And so at 0.6 you're kind of in the red range, and so we've got a red sandpit, has a high degree of reflectance. In other words, the red color is not absorbed, it's bouncing off, making it look red, where the other colors are absorbed. We move on over to 0.8, which is out a little further, and all of a sudden the grasslands are starting to get up much higher, the piney woods are higher, and the sand is lower, and the silty water is even lower still. Certain features in certain things allow it to absorb different energies, and that's kind of what this is. Once you establish a signature for a particular thing, you have an idea of what wavelength or area to look at, and then that can help you identify that object. And here's what we're talking about. This is the idea of creating something like a band ratio or an indexed value. The vegetation index looks at the near infrared and the visible light, and it calculates a ratio one to the other, and you can see how the trees look very different different times of the year. So we can use this normalized difference vegetation index to look at all kinds of stuff. Here's an example of looking at Africa, and you can see sort of as the rainy season moves along and it gets greener and greener and greener, right up until we hit sort of the Sahara Desert. Thinking of the history of all this stuff, we began collecting it some time ago. For example, NASA was established in 1958 to kind of keep track with the Russians, who put the first man, the first dog, the first whatever it was in space always ahead of us. By 1960 we had our own spy program called Corona. It ceased in 72, not the spying, the Corona program. And we use this to identify things on the ground. In terms of satellites, we have ones with geostationary, near polar, and sun synchronous orbit. Geostationary rotates the same speed as the Earth, so they basically don't move. Near polar rotate roughly North Pole to South Pole. multiple laps a day. Each path covers something called a swath, which is just the area that it looked at. It takes multiple days to get a complete coverage around the planet. Sun synchronous go over the same location at the same time every day. That allows you to get consistent lighting, which is useful sometimes. Just for reference, the Landsat satellites, you're looking at 8 to 14 passes a day, and they're 185 kilometers wide. And so that's the ground track, that's the near polar orbit, and that's kind of what we're looking at. And here's an example of how many days it might take to actually fill things in, starting at day 1, and you can see where day 2 and day 3 go, all the way to day 4 and 5 and 6, and eventually by day 16 you've kind of covered all of the area. Remote sensing satellites, two primary types: a cross track and a long track. A cross track is something called a whisk broom, where the sensor moves side to side. A long track is more like a push broom, where it just moves straight ahead. Resolution is important. Here we have the exact same location collected with 3 different sensors at 3 different resolutions, and as you can see, the better the resolution, the easier it is to identify things. Here's just a nice table that shows all the different bands from all the stuff. And when we look at remote sensing and we're looking at particular locations, it's good to remember that we identify locations that the satellite cover and how we download data in terms of rows and paths. And you can see path 18, 19, and 20, rows 31, 32, and 33. And so if you know the row path location of the spot you're looking at, it helps you sift through the data. Z value is elevation. It's the 3rd coordinate. Vertical datum is where 0 elevation comes from. Topo maps show landscape and terrain. DRGs are digital raster graphics. These are basically scanned topo maps. A geotiff is an image, but it has some spatial information. Contour lines flow along an image at a set elevation. We can also do a lot of really cool stuff in 3D. This is a 3D model of a location where we've taken aerial photos and a digital elevation model, draped the photos across the elevation model to give us this photorealistic 3D simulation. This is what topo maps look like. Each of these lines follow around. You find a spot there, a number like 1800. If you follow that line, everywhere on that line it's 1800 meters elevation or feet or whatever. And then if you figure out how far it is from one line to the next, you can do the breakdown and figure out how far each line is and what those numbers should be. When we look at things like a contour map, a topographic map, the collar is the area around the border. It has a lot of useful information, coordinate systems and whatnot. Digital elevation model, a digital terrain model, digital surface model, they're all rasters with elevation, and they're all DEMs, but a digital terrain model is the actual ground. Digital surface model is the ground and whatever is on it, so that would be like the roof of buildings as opposed to the ground level. A lot of times we collect this with LiDAR, laser-based technique to use to measure the surface. All this information and others is available through something called the NED, the National Elevation Data Set. Allows you to download a DEM for pretty much everywhere in the US. A viewshed is just like a watershed, except it's based on site. So from a DEM you pick a location and it identifies physically what can or cannot be seen from that location. We also measure a lot of other physical parameters from a DEM, like slope, which is rise over run. We measure aspect, which is the direction of the steepest slope, and we do hillshades, which basically amounts to nothing more than fake shadows. So here's 2D, 2.5D, 3D. We really don't make 3D stuff because we don't do holograms. We take a 3D object and we create an isometric view to make it look like it's in 3D, but it's still just in 2D, and a lot of times that's called 2.5D. Here is an elevation model that's not done in raster. This is done with polygons. Triangles, to be specific. This is a TIN, a triangular irregular network, which has a fancy math component to pick out to define how and what size to make the triangles, and then it connects them to form a surface. Here we have a cross-track scanner from an aircraft that would be picking up information. Instantaneous field of view would be the area underneath each pixel and the data set that it measures, how much that amounts to on the ground. This is a digital elevation model, probably from LiDAR, of a volcano, and judging by the fact that most of the cone's missing, I'm guessing Mount St. Helens. Elevation model, slope, aspect, these are typically what they would look like. From that, each one is a derivation of the other.